Hi guys, this is Mrs. Gastler, and in this video we're going to talk about work and kinetic energy. Now, kinetic energy may or may not be a bit of a review for you, and so we're going to kind of start at the beginning. Kinetic energy is the energy of motion. So we talk about it like it is the energy that an object has because it's moving. So you have to be moving in order to have kinetic energy. If you're not moving, you don't have kinetic energy. Moving objects, there we go. The faster you're moving, the more energy you have, the more kinetic energy you have. The slower you're moving, the less kinetic energy you have. And the formula we saw at some point in time is so we use, let's start with the beginning. K equals 1/2 mv squared. And we'll talk about the units here in just a little bit. And so the question is, so here we have v is for velocity. We've seen velocity before. Velocity has direction, but when we put it in this energy formula here, kinetic energy formula, we're squaring it, and so it ends up not mattering what direction it's going, so nobody cares what direction you're going. When we square it, the direction falls off, so we're really just caring about the magnitude, so it's really about your speed, and it doesn't matter which way you're going. And because of this squared, that means it matters more than anything else in this formula here. The half is just a constant, so the m stands for mass. So your kinetic energy depends on your mass and your velocity. So you can have more mass or more velocity, but velocity matters more. So increasing your velocity gives you more kinetic energy than having more mass does. Okay. So what does that have to do with work? Well, let's start, excuse me, at the beginning. And I'm going to kind of start over here. Okay, that way I have plenty of room, and I'll write some notes over here, okay? All right, so work is force dotted with distance when you're dealing with vectors. And we're going to talk about things that are going in the same direction. So we're going to talk about in the same direction to begin with, just to make things a little easier, and it'll extend to things that aren't going in the same direction. So for now, theta is going to be 0, which means that the cosine of theta is 1. Okay, so when we write FD cosine of theta, that really turns into F times D. Okay, so we're going to be doing FD. Okay. And we're going to think about what we know about these two things. And so we're going to use Newton's second law. And we're going to insert for F. So we're going to be looking at the net work done by the net force on an object that is being pushed some distance. And the net force is equal to the mass times the acceleration. So we're just going to stick that in there. So the net work makes you mad. Ha ha. No. Mad is the network. Okay. See what I did there? Mad. Okay. And there's several different ways we could go about doing this, but I'm going to go my favorite way just because I like it the best. And then if you want to see a different way to get from here to where we're going, I'm happy to show you because I really like deriving equations because I'm a crazy physics teacher. So just, tap on my shoulder and say, Miss Gastler, can you show me another way? And I'll say, sure. And then we'll pick a different way, okay? The way I'm going to go is we're going to look at the definition of acceleration, which is the change in velocity over time. So VF minus VI over T. And we're going to stick that in for acceleration. So we're going to have m VF minus VI over T. Okay. And we're getting closer. Our goal is kind of to get rid of everything. We want to see if we can't get this to look like something here. Okay. And so now we need to get rid of this distance. Okay. So we're gonna use and to do that we're gonna use the definition of average velocity, but we're going to have to kind of rewrite it. Definition of average velocity which I'm going to write like that because I'm too lazy to write out average velocity, which is d over t. But we're going to switch it around because we've got d right there. So d equals v times t. And we have to use the definition of average. Definition of average. Now, we actually already did this. This was a kinematic equation that we came up with. Whoops, average. And any old average, remember, is where you add them up and divide by how many there are. And we did this, we combined these already to come up with a kinematic equation that we wrote down that's not on the equation sheet. But I like this one a lot. VF plus VI times T. See? So we've combined these two right here. This one plus this one gives you this. And now we're going to stick this in for the D. Okay, so we've got M and VF minus VI over T. And now I'm going to put this junk in here. So 1/2 VF plus VI times T. Okay. Whew, that's my favorite part. This is fun. Whew, I love algebra. It's okay. You don't have to love algebra like I do. Okay, now I'm going to move some junk around. I don't know if you can see this right now. I've got an M here, and then I've got VF minus VI, and I've got VF plus VI. I've got a T on the bottom, and I've got a T over here, and then I've got this half sitting right there in the middle. So this half, this is multiplied by this junk and multiplied and multiplied and multiplied. So I can move things around because you can multiply junk in any order you want, right? So I'm going to put the half in front, and then I'm going to put the M next. And then I'm going to see that this T is on top and this T is on bottom, and that makes them cancel out. So I'm just not even going to write T down. And then I've got VF minus VI, and I've got VF plus VI. And now all I have to do is FOIL, which you thought you'd never have to do again, right? I like foiling, okay? But this is a minus and a plus. And I don't know if you remember the little cheating sort of thing, but it's, this one that gives you VF squared. Okay, whoops, we'll put this in parentheses. This is going to be minus VIVF, and this is going to be plus VIVF, and that's going to cancel each other out. And then this one is going to be minus VI squared. Okay, and then all I have to do is distribute this junk, and I have 1/2 M VF squared minus 1/2 M VI squared. And now, there it is. And if you didn't just go, oh, there's the kinetic energy, well then, poo on you. No, I'm just kidding. But that was really exciting for me. And, if you don't like algebra, it's okay if you didn't find that very exciting. But that right there is the final kinetic energy. And that right there is the initial kinetic energy. And so what we just did was we showed, this is all work net right here. We just showed that the work net is equal to the change in kinetic energy. So if we can find out what the change in kinetic energy is, or we know what the work net is, then we automatically know the other one. And what's also additionally useful about this is that I can flip this kind of around, and if I know what the force is and the distance is, then I can write those as equal to each other. So I can write the change in kinetic energy is equal to the force times the distance, right? Because I can substitute things in for the work net, and I can substitute things in for the kinetic energy now. So I can have, this equals 1/2 mvf squared minus 1/2 mvi squared. And if that was 0 or this was 0, then I have a handful extra equations that I can now write down that can simplify all sorts of things that I used to have to do in long drawn out ways of connecting these things on my own in kinematics, right? Okay, so we used to have to do things the hard way, and now that we have some energy things to work with, and we can do things like this easy shortcut way. It's not a shortcut way, it's just easier, right? There's less steps to do because the change in kinetic energy is equal to the work, which is this junk right there. So I can do less things, okay? Now, it turns out that if they're not in the same direction, I can still just throw in my cosine theta and end up with with a cosine theta in there, and it will still work out for my kinetic energy. This is just simplifying the situation so that I can see it a little bit better. Okay. I can still throw in the cosine theta, and it would just be hanging off on the end. I would put it on the other side, but that's how that works. Okay. We're going to do an example, which I had somewhere over here. There it is. Okay. So here's my example, and you might recognize this question. It's a similar question to one that was on a checkpoint at some point in time previously, and you had to do it the hard way, where you had to think about all this junk over here in order to be able to do this. And you were probably wondering, I don't have the maths, and now we'll see why. Okay. So at an accident scene on a level road, investigators measure a car's skid mark to be 88 meters long. The accident occurred on a rainy day, and the coefficient of kinetic friction was estimated to be 0.42. Use these data to determine the speed of the car when the driver slammed and locked the brakes. Okay, so we've only got two numbers there. What in the world are we going to do with that? Okay, do we even have enough information to find this out? I don't know. So let's draw a picture. Okay, a picture is worth 1,000 words in physics. And if you're not drawing pictures every time you're working through a problem, or every time a problem is really confusing, then you are shortchanging yourself. Draw pictures. Okay, so it's raining. There's some rain. Okay, here's the road. Here's a car. Okay, so it's going, and then it crashes. Here's a wall. I don't know what it will crash into. It doesn't say, but let's pretend there's a wall. Oop, there's a big wall. Okay, crashed. Okay. And it went 88 meters when it did this. Okay, and the coefficient of friction, which is that funky looking mu thing, is 0.42. Okay, so when I think about this from an energy perspective, over here it has kinetic energy, 1/2 mv squared vf vi. This is vi because it's initial, right? And over here it has no kinetic energy. Why? Well, it crashed. It's not moving anymore, right? Okay, so this guy is stopped. There's no movement, no kinetic energy, okay? Now, what made it stop? Well, it was the force of friction. Friction stopped it. Friction stopped it. I'm just making some notes here, okay? So the work done by friction, which was the net force on it, because if I draw a free body diagram for my car, the normal force was holding it up. Gravity was holding it down. Friction was making it stop. Friction, okay? Now, since the force is going in the negative direction and the car is moving in the positive direction and it's going to be slowing down, I'm going to have a negative change in kinetic energy. It's losing kinetic energy. So, and the force is in the negative direction. So my negatives are actually going to work out here, right? So when I throw in the cosine of theta, that's going to, the theta is going to be 180, which is going to give me a -1. So that's actually going to work out, right? So the work done by friction here is going to take away that kinetic energy, okay? So if I do FD cosine of theta, and my, let's see, it was final minus initial, right? KF minus KI. Well, that's 0, okay? This is -1. Okay, so I'll have negative FD equals negative KI. And my negatives are going to cancel out, so I'm just going to drop those, okay? So this is the force of friction. I should keep my little F there, okay? So the force of friction, that's in the equation sheet, which I do have right here. Although this is a different one, so it's got a bunch of extra symbols on it. But the force of friction is right there. Force of friction is mu times the normal. Okay. Force of friction is mu times the normal. And the normal here is balancing out gravity. So that's going to be mu. And gravity here, that's also on the sheet in case you ever lose it. It's over here. It's over here on yours. It's not over here on this one. That's the AP Physics C one. They don't get that one. But it says G equals FG over M. And if you solve that, that's just M times G, right? MG, okay? So that's what I'm going to be putting in over here. So this is going to be mu mg times d equals, and then kinetic energy, which we just wrote down over there, is 1/2 mv squared. 1/2 mv squared. Okay. Now you'll notice I didn't get the mass, but you'll also notice that I don't actually need it. It's on both sides. It cancels out too. I love when things cancel out. Physicists love when things cancel out, and things cancel out a lot, especially in energy. Mechanical energy has a lot of mass in it, and the mass cancels out like most of the time. Every now and then it doesn't, but most of the time it does. Okay, so mu gd, which I'm given this is a constant, I'm given that, okay, equals 1/2, that's a number that I know, and v squared. That's what I want, so I'm actually good to go, okay? So I just need to get this 2, with this 1/2 over there, so I'll just multiply everything by 2, okay? So I'm going to go over here. So I've got 2 mu gd and v squared. Okay, now how do I get the squared away? Well, I square root it all, right? Okay, so the square root of 2 times mu times g times d will give me v. And that's all I have to plug in my calculator. Okay, so let's see, that's going to be the square root of 2 times 0.42 times 9.8 times, where'd it go, 88. And that doesn't have units, that's meters per second squared, and that's meters. Oh good, I'm going to come out with meters per second. That's going to give me v. All right, does this calculator work? No. Okay, well that's a number. I don't have any calculators nearby. I have to use my phone. That'll be fun. All right, so let's see, 2 times, do I even have the square root button on this calculator? 0.42 times 9.8 times 88. That's 724.416. Now I got to square root that number. Square root. Where's the square? There it is. It's 26.91 meters per second. So that is how fast the car was going. That's a little bit faster than 50 miles an hour. Now, we don't know what the speed limit was on the road, so I don't know if that was speedy or not. But we were able to find the speed here by just plugging in a bunch of things. We might have been able to skip some steps if I wasn't trying to show you every little thing that I plugged in one thing at a time. And so you might have been able to do that faster, and that's totally okay. But that is how we can use, I should tell you what this is called. This right here is called the work kinetic energy theorem. And it's on the sheet somewhere, okay? It's on the equation sheet. Okay, so that's called the work kinetic energy theorem. And you can use it in situations where, I think you have to use it in situations where there is no friction. And that's it. All right, thanks for watching. Let me know if you have questions.